Python programmable source filters, and customization of Python. I will maybe do things in the reverse order. I will jump a couple of slides directly to this particular slide because it's a cute example I made up last month for the earlier tutorial. You know how Python has just a multitude of modules available for you. I use a lot of NumPy, for example. The scikit toolkit is also something I tend to use more and more. And I found this nice example from scikit-learn.org on clustering. And I thought, hey, you know, I could do that. I could do the same thing in ParaView. So would it not be nice to be able to use one of those existing Python packages directly into ParaView? Because then we would have the best of both worlds. The Python world, which is a huge community of open source code, and then the ParaView code. So I've taken an example from clustering on that particular page, and this is what I've done with it. So clustering is about taking a cloud of points in space, and then making clusters of neighboring points. So to do this, I use the Python programmable source. And the first thing I do, I reuse exactly as it is, the make blob module from the samples generators of the scikit-learn package. I gave it 3 different centers, and this would be an exercise you can do for yourself using any of modifying those centers. Now, of course, this is going to run locally on your laptop, so you would have to have the scikit package installed on your own laptop, okay, to do the exercise. But all of those are standard distributions which you install normally very easily. So I define 3 centers. I define a number of points which is 100,000, and then I make this blob of data. And the result of making this function call here, using the centers and the number of points and a standard deviation set as this, is an array X, which can be indexed just like in normal Python fashion. The first component, X, column 0 is the X component of the coordinates of those points. Same thing for Y, same thing for Z. And this would be, I mean, those lines of code which are specific to Python, that's the first lines. And those 4, 1, 2, 3, 4, those last 4 lines of code are specific to ParaView. In the Python programmable source, and this is also very well documented in the user guide of ParaView, so I suggest you do at least one time a reading of that guide. Okay, in the Python programmable source, I have a predefined object called output. So there's no secret here. This output, I did not define it anywhere else. It is predefined, and it's the name of that VTK grid object, which will be the output of the Python programmable source. Another predefined name is points. Points is exactly what it is, the array of coordinates for the vertices making up that grid. So here we have something very simple. From the Python module, we get an X array, and big X here an array of coordinates, and I just pass it exactly as it is without any modification. It's XYZ, XYZ, XYZ in that particular order. I pass it to my ParaView output. And then those 3 lines here are optional. This is just an example to show you how I would define a scalar field called X with the X coordinate of the particle so that I can color the blob of the cloud of points with the X coordinate. The same thing with Y, the same thing with Z. So imagine now that you would want to show the distance of those points from the center of the world, 0, 0, 0. You could use NumPy to do a computation of the magnitude of the square root of X component square, Y component square, Z component square. That would be your distance. This would be a NumPy array, and then you would put that into output.pointData.append, and you would attach that NumPy array to the output of the Python programmable source. So that's basically how it is. The Python programmable source should not be too intimidating. There are predefined words, output. Input is another predefined word. Actually, it's inputs with an S because there can be multiple inputs. Points is predefined. Point data is predefined. So once you learn a couple of those examples, then you have it. And then if you know how to program things and how to manipulate Python arrays, then you are pretty much ready to go. So this is the setup of the demonstration. There's one little trick, if you want, because we're dealing with a cloud of points. If you only read points in ParaView, you cannot view them directly. They're there, but you get an empty screen. Unless you use the point Gaussian representation, which is something we have not talked about yet, but I will, during the demo, I will show you the example. Anyway, so the trick I use is to define one cell of type polyvertex. So this is a single cell to which I can attach as many points as I want, and by this I mean really a lot. I've done the experiment once with hundreds of millions of points, and I could not manage to crash ParaView. So it just worked. There's apparently no limitation to the number of points you can attach to a single cell. So this is the Python code I use for creating that cell. This is those 6 lines of code I have copied and pasted them in many examples I have done in the past. It's really just a template you can reuse pretty safely. So defining your number of points here, you create this ID list, which you set very easily like this, 0, 0, 1, 1, 2, 2, etc., all the way to the end, and then you insert that cell of type polyvertex. That is an optional part, but it's very useful to view your point in ParaView. Now, to do clustering, ParaView has its own module, and it's called k-means. I've had some difficulty to use k-means, actually, and this is why I was motivated to use what I thought would be perhaps a more robust implementation, and I used the scikit toolkit. So there's my code, import NumPy as NP. From the cluster module, I use mean shift and estimate bandwidth. And by the way, I didn't have to invent that. I got that from the web page. I just showed you that earlier. Okay, so I really didn't have to study very much that particular instance. There is, again, my input definition here. So this is the predefined name in the Python programmable source and filters. And the points array, we've already discussed that. So since it's a Python array, it has a particular shape, and shape of 0 is of course the size, the number of points available. I decided for that example to take a number of samples that's 1/10 of the overall sample. And there's the demonstration. So I'll jump straight to the demonstration. And we're going to explain what we're seeing here. So first of all, the points themselves. The points are over here in 3D. Okay. There we go. And I can color with the x coordinate over here, and that looks correct. Yes. Because x is pointing like this at the current time, or I can color with y, zeta, or etc. Good. If I show you the output of the ParaView k-means filter, this is what I get. So ParaView identified those 3 clusters of data, but I was a little bit bothered by those points over here belonging to the white cluster, although to me it seems like they are much closer to the blue cluster of points. This is why I wanted to try this alternate solution. And the alternate solution is here in my programmable there, and now I have the same analysis here with 3 different colors, and I get what I thought was a little bit better clustering solution. Okay, so there is really a motivation for using directly the Python algorithm. So let me go through the source code that was used for that particular demonstration. From the scikit learn toolkit, I generated data using make blobs. Given 3 centers, I generated 100,000 points. And I assigned them to the output of my programmable filter. And I'm going to point out now some interesting things about this programmable source. There's the source over here in the pipeline browser, and there's the output dataset type for the source, and the type is VTK polydata. Now, what is important is that depending on the type of grid you're going to generate, there will be a different set of predefined objects. Because I use polydata, which is a perfect type for a cloud of points, the points object here is predefined because I have an explicit list of coordinates. In the case of an image data, for example, and I'll show you here that I can have multiple, basically all of the types, all of the primitive types for ParaView, I can generate here. Depending on the type here, I will not need an explicit list of coordinates. For example, VTK image data, the only thing that is required to define a Cartesian grid is the origin of the volume and the endpoint. So in that case, I define only those two numbers and I don't have an explicit list. Okay, so in this example, I have polydata and points over here is defined as that particular object. If I look at my information tab, I have exactly this. One cell, 100,000, 100,000 points available. And I mentioned earlier something about the cell ID. I'm going to remove that. Now, because I modified the input of the pipeline, it has to regenerate itself. But what I wanted to demonstrate is that given a particular input, you see now that I have 0 cells and 100,000 points. I don't see anything on my screen until I switch to the point Gaussian representation, which is something we haven't seen earlier. And there's my point again. So what is the point Gaussian? Something pretty neat, very powerful, because it draws a little sphere on the screen for each of my 100,000 points. And you can tell that it's pretty damn fast. Why is that? Because this is done directly on the GPU. And I cannot show you a wireframe representation of those because there is none. What we're looking at here are not spherical objects, but it's the image of a spherical object, very small, a few pixels, but it looks very nice. It's the image of a spherical object thrown out on the screen by the GPU. So this is why it's so fast.
So if you change the view,
look, I can change the view.
will not change.
No, you see?
Wow. Yeah.
And if I go very fast, you can kind of tell at times that it looks quadrilateral. It's exactly that. It's that little image. So in theory, in fact, it's just, let's take any one of those. Here we have one little square image representing the sphere, and then it's transparent on the border, and the GPU is so smart that it knows how to accumulate all of those. So that's one good way to do rendering of points. There we go. Now I'm a little bit lost with all this. So where am I again?
I have a question.
Yes.
So the only difference I can see from points and points Gaussian is that this Gaussian makes it, I don't know, slightly bigger sphere.
Yeah, you can change the radius of those spheres at any time using the graphical user interface here. It's rather simple. You go to your properties, and you have a menu.
Yeah, but this is really the point of making an option of just points and another option for points Gaussian. This is the only, I don't know, objective of doing this.
You know, I'm not sure anymore because I see now that my output over here. No, my output is, yeah, I was confused because I didn't see the output of the clustering, because the output of the clustering inherited the fact that there's 0 cell. So the answer to your question is yes, in that particular case, the only real purpose of adding the cell would be to be able to show the points as a point representation over here instead of a point Gaussian. So if I switch this to point, I still have an empty screen. If I switch to point Gaussian, there is my cluster of point. Okay? There we go. And those point Gaussians are really nicely defined. It gives me a nice crisp pictures that I like very much. So I recommend using that particular option when you can.
Can I also ask a question about the script?
Yes, I was.
From programmable source 1.
Yes.
So it's got some code inside.
Yes.
When you go inside the code, you say that this output is a predefined word.
Yes, right here.
And it has object points.
Yes.
It's also predefined.
Yes.
But it is defined before saying that it is a polygon. And you say that this points is an object of the polygon type. So, I mean, from a programming perspective, so you put points, object, before you saying that this output is a polygon type.
What matters is that your intention is given before you hit the apply button. Because here this is just a text file. Nothing gets executed until I push the apply button.
It's executed line by line. It's a normal programming.
Yes, that's true, but it really depends on the fact that I have defined here polydata as my output type. If I were to, and this is the default by the way, if I were to say image data and apply, it would give me an error. It would tell me point is not defined. Let's try it. Well, sure enough, object has no. We can't read everything because it's object has no points defined, or it shows most likely on my console output. There, object has no attributes, points.
And then you say that this is a polyvertex.
Yes.
And you say that it is default, but it is default because it's written somehow in the script, or it's default in Parameter?
No, what I said is that the output type over here of the programmable source uses the VTK polydata as a default value. That's what it is.
And for example, if I'm loading the script,
If I have?
If I'm loading the same type of scripts,
Yes.
and then I want the script which uses another data,
Yes.
different from this polyvertex.
Yes.
It means that when I'm loading this into ParaView, it will give an error because I'm loading the object which is not the default to ParaView.
So here we have a programmable source, which by definition does not take any input as a source. And I like this question very much because then the second part of my pipeline, let's just finish up with this there. The second part of my pipeline is the programmable filter. And in that case, look at the input, look at the data set type. I have the default value, which is the same as input. So if I feed a VTK polydata, it comes out a VTK polydata. If I feed a VTK image data, it comes out as an image data. So this is one option to inherit the type of grid that you put in as an output. You can also modify that, and in that case, you have, again, the same choice of options here. But this is because it's a filter. The source itself does not take any other modules as input. Okay? It takes a little bit of practice with it, and then after you've seen a couple of examples, it will be easier to work with. So there is my programmable filter. The input of it is the programmable source. So my clouds of points over here is defined as input 0. And because my cloud of points is a VTK polydata, I know that it has that predefined name called points. And those are the coordinates of my vertices. If we go back to something I went over pretty quickly yesterday, for each of the grid types, I have put in the slides an example of how to generate a structured grid, how to generate a rectilinear grid, etc. At least up to this. And by the way, see, I also have here a type VTK molecule. So reading from an ASCII file a list of atoms coordinates, X, Y, Z, and some properties associated with the atoms, I can use NumPy, load from text, or what is it called, gen from text, reading an ASCII data set, and I can create my molecule right there on the fly using some custom Python code. I'll show you an example of this later on. Back to over here. Since polydata is defined, I inherit my array of coordinates from my inputs, and then I pass it to the bulk of the Python analysis, cluster analysis. The output of it is two things. From the min shift Python package, I get an array called labels, but that label is a set of cluster ID for every point. And what I wanted is a unique set of labels. So I just use NumPy. Again here, NumPy.unique on that labels array to get my particular set of clusters. And then I added this. As you can see here, my output is the predefined name for the programmable filter. Point data is where I associate scalar field with it, and I append the labels array and I call it cluster ID. What is missing from this computation is the computation of distance. I mentioned that earlier this afternoon. So I use NumPy again here for all of my clusters. I will get the distance using NumPy linear algebra norm of that particular, the particular coordinates of my point minus the cluster center, okay? This is where the cluster center, by the way, is another, where is it? It's right here. It comes out of the min shift module. So doing this, I'm able to calculate for every point its distance from the center of the cluster. And again, I append that as a distance field to my array. So at the very end, this is what it looks like. I have here my cluster with two different scale fields. One of them is the cluster ID, one of them is the distance, and if I color by distance, that's what I get over here. I have this display where from blue to green, I get the distance of every point towards the center of its own cluster. It would be interesting here to actually take this and slice it in two, like this, using perhaps the x normal, no, the y normal, yeah, interesting. I get an empty output because I don't have a cell. That's what I tried to do, but it didn't work because I didn't have cells. So this is the way to do it. You do a glyph of type 2D glyph of type vertex, which is this again, and then you clip that particular object instead. Change input glyph, OK, turn that off, and now I have my distance over here. I turn off my plane, and there I have, as you can see here, oops, quite well, I have my clusters. One of my clusters is cut exactly in half with the distance showing off very well. And you see, when I use single points, when you zoom in, it's impossible to see. So it's a lot nicer to use point Gaussian. And why does this one doesn't work? Because of? This is pretty strange. Oh, it could be because the size of the Gaussian, yeah, okay, very good. That's often, the size here is set to 0. So if I set that to something, I don't know why this default is not, okay, so that's too much, obviously. If I do 10 times I do half again. There we go. I have my nice display of the clusters with the points colored by distance. Okay, so this is an error I've seen quite often, actually. It's unfortunate. This Gaussian radius here gets set to a 0 value. So if you don't see anything on the screen, you should have the reflex to say, oh, I need to check the size of that particular setting here. And since we're at it, the shader preset, here's the sphere. If I change that to a square outline, for example, see what I get? A triangle, a plain circle, a black edge circle, or the sphere. And now you can tell they're really just tiny little miniature textures that are sent out by the GPU to do my rendering. Okay. So this was the idea with the programmable source and the programmable filter. Now, one of the inconvenience of those is that you have a text file here with Python code. But for example, here the number of points, you'd like that to be something showing up on the graphical user interface. It would be much nicer. It would be a lot more user-friendly. So I will quit this and return to my presentation. And now that motivates the lines that were just before it. Right at this address, which is the GitHub address for the ParaView development, there is an example of a Python algorithm. So this is written in Python, and that example shows you how to add the so-called decorators. Decorators are some things that elements that will show up on a graphical user interface, and it will take you away from the source code editor and lets you interact with your Python program directly from the graphical user interface. So here's the demonstration I have prepared. There's a couple of examples. One of them was the rectilinear grid 1.py. So I'm going to run that example first, standalone, and I will show you how I integrate this as a Python programmable source, and then how I can make the graphical user interface of ParaView, how I can modify the execution of this filter from the graphical user point of view. Basically, the source code needs to be modified. There's a couple of lines of code, and I will distribute this example, so you'll be able to exercise that. I add those couple of lines of codes to define my Python image source as a source for ParaView. I comment out the MPI-4Py lines of code here because ParaView has its own MPI layer for the parallelism. And then the example takes the dims array with a custom, not a custom, but a default value of 11 cube. it uses this as a vector of integers, and those two lines of codes, they publish, if you want, the input on the graphical user interface side. So let's see if I can rerun that demonstration. This is a distributed. First of all, I have to find what is the code called again. It's called distributed image data. So okay, this is my original code here using MPI. And the definition, what is important for us, is that the definition of this rectilinear mesh, no, actually, I'm sorry, it's not rectilinear, it's image data. Here's the type. It takes the spacing, the origin, and the global extent. Remember yesterday our discussion about the extent? It's really the set of indices which we say ParaView can generate. There. So if I run this with PV-Python, for example, it doesn't create any output because there should be a tester that goes with it, and I don't have that tester. And I think I have multiple versions of it. I will check for it. There we go, I knew it. I knew it. VTK distributed test.py PV Python. There it is. So there is my image data of size 31 cube. Okay, here's the global extent is what is advertised during the first pass of execution. And because we're running on a single processor, the update extent is exactly the full size of the grid. All right. Can I run this inside ParaView? Here's my code. I'll have to check. Okay, it's an image source, so we're cool about this. I'm going to run this Python programmable source. As a source, create a Python programmable source, and no, this is stupid. I shouldn't have done that. I should go directly to run script VTK test. Okay, there it is. There's my grid. but I wish to have here in the graphical user interface, I wish to have the same grid type. Well, you have to be a little bit patient with me. I have to do exactly what I said in the course notes. I make those two different lines here visible. I comment out everything else that has to do with parallel with MPI for pi. And I think we're done with this. I run ParaView. And now, in my plugin menu, Manage Plugins, I will read this particular plugin. I will read this particular plugin. VTK distributed image data is there loaded for me already. So from my Python menu, I can call a Python, there we go, Python, what is it called? Let me put back my glasses here, I don't, a Python annotation calculator. I used a different name, so I have to go back to my distributed image. Python image data source, that's what it's called, image data source. So, well, something is not, I don't see that data available, which is kind of strange. Aha. Never mind. Load, manage plugin. I will remove this plugin and load this plugin right here. Still, I don't see it. This is not right. Yes, I heard your suggestion. Yeah, this will be. Let's try this one. VTK rectilinear grid. And the address is VTK Mesh Builder, okay. And now we have a we have a Python. Again, I don't see those. This is pretty strange. More VTK, rectilinear grid 1, Python rectilinear grid source. Oh, actually, yeah. Well, something is not working anymore on in my demonstration. I'll have to take the break and to fix it. what I'm trying to achieve is the following, is that something you define inside a Python programmable source or filter can become a plugin. And in that case, you load it via the Manage Plugins menu, and then you execute it just like a normal ParaView source or filter. Well, looks like the example provided by ParaView is working, so it's already loaded, and it's the one I have here, and the Python superquadratic example. So let's just run this. This is the example from the notes provided on the GitHub repository for ParaView. If I make this visible, I have here an object which I can modify through that graphical user interface. So for example, changing the resolution, etc., etc. So there, I will probably do best to go back to my notes. Okay, that is the example. And we can discuss it from the particular example. Okay, Python algorithm examples, fine. It doesn't want to cooperate, so I know where to find it. Python plugin. No, Python Qt. That's not. Okay. Adios. No, I don't find it anymore. Python algorithm examples. Of course. All right, so this is the example provided by ParaView, which works better than my example. There is a Python superquadratic source, which should have a particular label, and that's right here, Python-based superquadratic source example. If I go to my ParaView shell, this right here is the name of the plugin I have used, Python-based superquadratic source example. And the graphical user interface is the following: a center, a slider for the resolution, a scale, a string, etc. We're going to find exactly those parameters in the Python code. So there, I think we almost have it. We almost have it. There it is. The first decorator, so you define the center as a vector, a double vector property of size 3 with a particular setting command called setCenter, a default value of 0. That's for the first one, the first example. The scale, here's another example. The scale method is advertised for the graphical user interface to become a slider. The theta resolution is right here. The phi resolution is right here, etc. So, there I have them exactly side by side. Those are the definitions using those SM property decorators. This is how you advertise the Python commands back to the graphical user interface. And once you have this defined, okay, there's one each for all of those different value. You can use the algorithm as if it were a compiled filter provided by ParaView. So I apologize, this was a little bit complicated because my example didn't work anymore, but the example provided here is a good illustration of it. If I go back to my source code, there might be, so this is the Python superquadratic example. There might be a second example I forgot. Yeah, there's a reader example called a Python CSV reader. There we go. And it reads a list of comma-separated value as a Python object. There is the famous NumPy gen from text, which I mentioned earlier. This is how I read an atom description, X, Y, Z, and atom species, and so on, into ParaView. I'm using the same example here. You also have a writer example provided, which would write NumPy compressed arrays to the disk there. Anyway, the moral of the story is that you can write a customized source or filter using Python code, and then you can import that into ParaView, and you can expose the graphical user interface for it. When I save the state of this particular example to a Python file, I'll show you what comes out. I forgot where I saved it. Is it over here? No, it's not. It's over here. No, it's not either. I'd have to redo it again. Python superquadratic example. Over here, I show it. Then I save the state. And in my Python code now, I have here my Python-based superquadratic source example looking just like any other ParaView filter or source. Now, what would be missing in that Python code is the load plugin instructions, because by default, if I show you my ParaView in the manage plugins menu over here, those Python algorithm examples are loaded by default. So this is perhaps the last trick I'm going to teach you, is to look for Py code and there it is. There are some examples of it. I have multiple examples. One of them here loads a plugin using XML code, okay? And I'll show you the content of the XML code. If I have it over here, Python molecule XML. There is a description in XML code to add functionality that is present in VTK, but that doesn't exist in ParaView. If I know the name of the class, in this case it's VTK simple bond perceiver, I can define it as an XML description and load it as a plugin. Now this looks very complex, but you don't have to learn any of that particular syntax. You copy from the examples given by ParaView. ParaView itself uses a list that is exactly like this to load the predefined list of a VTK class. And to show you an example of loading a plugin as Python code. Here, load plugin, I've left it empty, but you would put here the name of the Python code for the Python rectilinear grid source. So this is my object defined as a Python code over here. In this VTK this is what I would write to load my plugin as a Python code and then to use it later on in the text. So as soon as the plugin is read, then over here I can use the object as a regular Python object. Okay. I'm making confusion here, dot pi. Is this the correct file name? I'm not sure anymore. Aha, good point. Rectilinear grid 1, that's what it's called. Shame on me. Okay. It says it's not defined because it's missing a global PV Python. Here's how to find out what's missing. From ParaView, simple import stuff. So it's not simple anymore. Eh? And I do a dir on load plugin. And I do help there. And it's missing ns equals global. There we go. And if that doesn't work, I'm ready to give up. There we go.
Yay.
My goodness. So I have a rectilinear grid. And I have right here the dimensions of my grid, which I can change like this. Okay. There's no coloring to it. There's no scalar field. This is demonstrating that from a Python code, using the programmable filter of ParaView, in fact, the programmable source, I can attach this programmable source to a graphical user interface, to the graphical user interface side, and then modify directly the parameters of the Python code through the graphical user interface. Now, if I run this in parallel, we will do the exercise because now it's working, and that will be the finishing point. If I use MPI and 4 nodes, I'm not sure I had to click apply or not. Apply OK. Here's OK. This is an error I do very often. If you run in parallel, it's like you either have to give the full path of the script or else you load your data from over here. Okay, there's one more error in that because we're doing client-server now, we need to load the plugin on both sides of the computation. So bear with me. We have it here. Loaded rectilinear is over here, and then over here as well, rectilinear. So this is the wrong place. We need to go to VTK mesh builder, rectilinear 1, loaded, OK. Still no luck. Victi problem loading the plugins. Oh, it says no such file. Okay. Oh, you have to give it a full path. Oh my goodness. Yes. Copy. Because it's distributed, ParaView doesn't know where to find it. Good grief. Okay. So I'm running on 4 processors, and this is my subdivision. Now let's play with it. Let's put 111, and we'll see what happens. This happens. Let's put 11 and 150. Not too big, because then we don't see anything. 36. Apply, and see how every time ParaView decides on a different mode of distributing the computation. Well, thank you so much for your patience, because I got lost here in my example and things didn't work out as I had it prepared earlier. So there we are on 4 processors, and we're running a Python code that was distributed, that was integrated as a plugin, and for which we defined a user interface. Here it's very simple interface with only the DIMS input. But we have a nice button here, reload Python module. So this is very nice, because it allows you to interactively prototype your plugin. You can use an editor to change your Python code. If you see something wrong with it, you modify your code and you reload while you are in ParaView. And that works really quite well. Okay, so there, this is time for me to stop, because I've made a few errors this afternoon. That example from GitHub would be your starting point. The example we just showed now of creating the rectilinear grid, I will clean it up, and then what I will do is I will update the notes, okay, with the full example, and this way you'll be able to do it. Basically, this is about adding the decorators to ParaView. So there's the example of the set dims, exactly as we have in the example. We've seen the example of integrating Python code from the Python scikit repository. And with this, I am finishing here for this afternoon. So thanks a lot for your patience. Now, we have 20 more minutes of time, actually even more. I'm happy to stay here another half hour for you to answer any questions you may have on running this particular example or any other questions we touched upon.